Today I will talk about our recent result about the sunflower lemma, improved sunflower bond. Let me start and first introduce some basic notations. Say we're going to first introduce what is the sunflower. Definition. Sorry. So we are first going to introduce what is the set system. We have a ground set, so let S be a set, X be a set. So we call it a ground set, so just a set. Now a set system on X is just a collection of subset of X. Set system it's just a collection of subset. So this is a set system. By the way, please stop me if you have any question. I hope everybody can follow this talk. I think the proof is pretty simple. We call this a W set system. If for every S in F, the size of S is upper bounded by W. I hope this is clear. So this is the definition of set system. Now we're going to introduce what is the sunflower. A sunflower structure was introduced by Edelsch and Rado in 1960. Sunflower given a collection of sets S1 up to SR. So this is by T. We call this a sunflower if for any I and J, the intersection of Si and Sj is exactly the intersection of all sets. So this is the definition of sunflower structure. So we call this our set system our sunflower if we have this property. We can draw some. We can say check some example. Say for example that S1 is equal to x1, x2, x3. S2 is equal to x1, x2. Say for example x4, x5. S3 is x1, x2, x6. Now at first, this is a four-set system because the largest set is S2. It contains 4 elements. So this is a four-set system. And then this is also a sunflower because x1 and x2 are common elements on every set. And then by removing this part, the remaining thing are disjoint set. We can always draw a picture. It looks like a sunflower. Then that's the reason we call it a sunflower structure. X1, x2, x3. This is x4, x5, and this is x6. So this is a sunflower structure because we can always draw. It looks like a sunflower. So feel free to stop me if I have any question. This sunflower structure has a lot of applications in both extreme combinatorics and theoretical computer science. And in the same paper, this paper, Edelsch and Rado proved the first sunflower lemma. Is that say for any R is larger or equal than 3. And F be a W set system. If the size of F is larger than factor of W, and R minus 1 to the W, and F contains R sunflower and R sunflower So what it means is that say if we have set system f that is large enough. How large it is? It's larger than a factor of w times r minus 1 to w. Then we can then f contains the sunflower, which means we can find our sunflower, which means there exists S1 up to SR is a subset is a set from f, and this set forms a sunflower. Okay, in here we want r to be larger than 3. If r is 2, then it's a kind of a trivial thing. So we care about r is larger than 3. Okay, so this is the sunflower lemma, which was proved by Edosh and Redo in 1960. Okay, okay, so this structure has a lot of applications in theoretic computer science and combinatorics. Okay, then what is the sunflower conjecture? Okay, in this talk, we're going to focus r is equal to 3, because for r is equal to 3, this lemma is not trivial and it's pretty hard. So let's focus on only r is equal to 3. But our result can be extended to any arbitrary r. Okay, so this conjecture is there exists a constant for any r larger than 3. There exists a constant c that depends on only r. If the size of f is larger than CR theta w, R sunflower. Okay, so this is a conjecture, also conjectured by Anderson and Redo. Okay, the bound so far is factor of w times r minus 1 to w. Think about r is equal to 3, then this bound looks like w, roughly this thing, roughly w to a w, and the conjecture was constant to a w. So there is a bigger gap between the conjecture and the lemma so far. Okay, so this conjecture has a lot of applications in theoretical connection. It has a lot of connections about theoretical computer science. For example, some sunflower structure gives some result about monotone circular lower bound and matrix multiplication, and also data structure lower bound and a lot of things. So this is a pretty nice conjecture. And also, Edosh raised 1,000 here. That if everybody solves this conjecture, you can get 1,000. Okay, so what is the best result now? I mean, best result before us. The best result. Okay. Yeah, the before us was by the 2000. Okay, the bound, I just wrote the bound here. Say for r is equal to 3, and if f is larger than w factor of w times log w over log w to the w, then it contains a r sunflower. So basically, this is roughly like w to the w minus little ow. So the best result so far, I mean before us, so just a slight improvement in the exponential part is minus a little ow. Okay. Now, I want to claim, so now then I want to state our recent result is that.
Fukuyama, you could probably say Fukuyama first, right? Fukuyama.
Yeah, but it's not a peer reviewed result. I don't want to.
We think it's correct, right?
No, recently people found some bug. So there's still debating here. Okay, there's another result. There's another result, but which is not peer reviewed. It's just posted on ICAP. We're still verifying that the proof is correct or not. It is about such like, I mean, w to the 3 4 w. Okay, so there is another result. Is get this bound, but we don't know it's correct or not. We're still verifying that. Okay.
What's the year?
It's about last week.
2018, right? Yeah.
I forget. Yeah, maybe. Yeah, actually, yeah. And okay, so yeah, I don't want to mention it now. Yeah, who's okay? So all the recent lemma by Ryan, where is here? Is that for any r? So actually, our result is for any r. If f is larger than log w, hence r w plus little o1, then it contains the sunflower. Okay, so our recent bound is that we improve this major part, the factor of w, we improve it to log w. Say if r is 3, then it's roughly like log w to the w. So this is our recent result. Okay, so this, okay, so yeah, so here is roughly w to the log w. We improve it. Okay, is there any question now? Okay, so this is our result. Okay, in order to prove our result, I'm going to introduce some basic notation. So I want to introduce our main framework is about the pseudo-randomness and the structure trade-off. Okay, now we're going to define the link. Definition of a link. So these are common definition in the set system. Okay, so for any t subset of xt and f is a set system, we're going to define the link of t as this set system is s minus t and s e. Okay, so given t, we're going to define the link of t is just basically we're going to take all of these sets that contains t as a subset and then going to remove this t. So this link, we can check this example here. So let's say f is this set system, and we can take, for example, you can take x2. Okay. The link of x2 is just, is this clear or is too small? Anybody? Oh, it's okay. Okay, sure. Okay, so basically the link is just x1, x3, right? Because the first element contains x2, and then we're going to remove x2. And then the link here is x1, x4, and x5, and x1, x6. Okay, so basically, because every set contains x2, then we're going to remove it. But if we're going to take, say, for example, x3, then the link becomes much smaller. For the x3, x3 is just x1 and x2. Because only the first set contains x3. Now we're going to take it and then removing the x3. Now this two sets does not contain x3. Then we're going to throw out. Okay, so this is the definition of a link. Okay, say why we're going to introduce the definition of a link, because it's pretty useful. We have a very simple claim is that claim if there exists a t such that if t contains Okay, so the simple claim is that if there exists a link T such that Ft, the link contains R sunflower, then F also contains R sunflower. So this is a pretty simple claim. All right. So for example, if Ft has set S1 prime up to Sr prime for the sunflower, then just by union T, then this is a sunflower in the previous set system. Yeah. So this is now we can just focus on check the links. Now then think about them. It's natural to it's very, very natural to introduce we call the pseudo-random properties that there's no such large link. Why? Because if a set system, if it contains a large link, now we can apply induction to this large link to find the sunflower. Because if we just want to find the sunflower, we can just, if there is such link, we can focus on this link. Now we are going to introduce the pseudo-random properties that say there's no large link. So this is just a natural way. It's a pseudo-random property. Okay, so basically this is a property we want to say there is no large link. We call set system F is kappa. Say kappa is a parameter. Kappa bounded if for every t the size of Ft, the link is upper bounded by kappa minus t times F. So basically, we want to say this is kappa bounded, which means there is no large link. If there is no, yeah. So this is the idea we want to capture the pseudo randomness. Okay, so this is the definition of kappa bounded. Okay, I want to say for the people who are interested about the communication complexity, say there is another name for kappa bounded, so which is called the block-wise mean entropy. So it has connects to the lifting theory. It's called the block-wise entropy. So, but I'm not going to go through more details now. So basically, this is the definition. We can check an example about the kappa bounded set system. Is okay. Example say that x1 up to xr w be disjoint set. Joint set of size x of each of size is relatively kappa. Then we can take this set system is that f. We can define this set system as x1 times xw. So basically, this is we are going to. So this is a combination of this set, and say we'll take one set from each set. x1, xw, xi from capital Xi. So we can take kappa disjoint set. Now we can define this set system by taking one element from each set. So the size of f is equal to kappa to the w, because there are kappa choices for each coordinate, then there are w sets. Total w. So basically, the size of f is kappa to the w. And we can check. We can just do simple calculation. Is that this is the kappa bounded? So this is the calculation. Okay. Okay. Now what we want to show now is so by the pseudo-random structures trade-off, we want to show this following property is. We want to show.
It also has a W sunflower, right? Because you can take
you mean this example? Yes, yeah. Yeah, this has W sunflower. Disjoint set. Yeah, exactly. Yeah, for this example, yeah. Okay, so now we can simplify our question. We want to show the following thing is that we want to find a kappa. And a kappa such that for any set system, if F is kappa bounded, then it contains so we're thinking about R is equal to 3. Three sunflower. So we want to find the smallest kappa. Okay, maybe this is depends on W or whatever. Okay, so if F is kappa bounded, then it contains a 3 sunflower. So it's a very simple claim that if we found this kappa, okay, so we can show, so it implies for any F, if F is larger than kappa theta W, then F contains 3 sunflower. Okay, so if once this has been confirmed, or I mean, once we find such kappa, then we can simply imply this result. The reason is pretty simple. Say, given F, if at the set system is larger than kappa W, to W, then there are 2 possible cases. One case, it is kappa bounded. Then by this hypothesis, we can show it contains R3 sunflower. Otherwise, just by the definition, if this is not kappa bounded, then just by that definition, where is the kappa bounded? Okay, here is the definition of kappa bounded. We can find a set sub T such Ft is larger than kappa minus T, right? Minus T, this is by definition, times F, which is equal to kappa W minus larger, okay, we can say minus T. Okay, so if this is not a kappa bounded, then we can find a large link such that this link is large enough, so larger than kappa to the W minus T. Now we can just run we can apply the induction because Ft is a W minus T set system because we threw out the T set. Yeah. So what we need to show to prove is that we find such kappa with this property. So this is our main framework. We are going to find this kappa. Okay. So please let me know if you have any questions so far. Okay.
You need kappa be increasing function of W.
Yes. Yeah. Ideally, we want this kappa to be independent with W. So we just want to find the relationship with kappa and W. If we proved kappa is independent with W, then we are good. Then we can confirm the sunflower conjecture.
We need to make sure it's increasing as a function of W, just so what you wrote works. And it is, but you know.
Yeah.
It's probably just good to mention that.
Yeah. Okay. Now, then our main work is trying to find such good kappa. Okay. So the property. Okay, all of the previous framework is pretty straightforward, right? You just now, with our lemma is that if F is 3 times log W, 1 plus lead O1, bounded. And it contains 3 disjoint sets. Okay, actually we proved something even stronger. Okay, say if this is 3 times log W, so theta 1 plus lead O1 bounded. then it contains 3 disjoint set. For any R, for arbitrary R, we can just simply replace R here, and then we can get R disjoint set. Okay, so let's focus on R is equal to 3 now. So basically, this lemma implies the improved sunflower bound. So just plugging off the previous thing. Oh, it's disjoint set.
But in some sense it's not stronger, it's, since you allow induction already,
Yes.
Then the disjoint set is what you find in a lid.
Yes.
Will recover you a sunflower with S or with some forward.
Yeah, good point.
Right?
Yeah.
So
Yeah, good point.
it looks stronger, but it looks, with the induction, it's probably
Yeah.
a natural thing.
Yeah. This is natural thing. Yeah, so yeah, this is not stronger. But actually, we can prove even stronger. But this is not our. I'm going to state our next lemma. Next lemma must be even stronger. Okay. Yeah, good point. Yeah, this is not stronger than sunflower amount. But we have something that is really strong. That's the reason we cannot improve the log W barrier. So because that structure is too strong. Okay, then we are going to define P epsilon coverable. Okay, so we say that the system F is P epsilon coverable if the following is true. If for random W there exists S if S not equal to empty set and S is a subset of W, it's larger than 1 minus epsilon, and the W, the size of W is P times X. Okay. Now this is the definition of coverable. I'm going to draw a picture. It will be much easier to understand what's going on with the definition. If I say, let's say we have X, the ground set X. Now we call F is P epsilon coverable if the following is true. We have randomly sample subset W. The size of W is P times X. Okay, randomly sample P fraction. Then with high probability means probably larger than 1 minus epsilon, we can find S is a subset of W. So with high probability it covers a set. With high probability it covers a set from this system F. So this is the definition of P epsilon coverable. Okay, if we just take this picture, I think the definition is easier to understand. Yeah, when I gave this talk, when I was first time to give this talk, I just gave this definition. People feel it's hard to follow what's the intuition, but then people suggested me to just draw this picture. So this is the definition of P epsilon coverable.
So it basically says something about the density of F, right?
Yeah.
It's just how many sets are in.
Yeah. If there's, if there is a lot of set, then this is coverable. Yeah. So.
It's like you take the up shadow of F all the way up to P times X.
Yes.
And you hope you cover 1 minus epsilon.
One set. Yeah. At least, with high probability. Yeah. With high probability, 1 minute that covers.
DNF interpretation of this.
Yeah, but I don't want to introduce DNF. There are too many notations.
So is what I said correct? You look at the subsets inside F. You take their upper shadow all the way up to size P times X.
Yeah.
And you need to cover all of the sets except for epsilon.
Yeah, it's right. It's equivalent.
Yeah. Okay. So basically, this is the
And do you want like exact size P times X, or do you want to sample?
exact. So we just take an example. Yeah, example KP exact set P. Okay. Okay. So this is the definition of P epsilon coverable. Okay. Now, why we're going to introduce definition of P epsilon coverable is that we have a simple lemma. Is that if sorry, I want to change the definition here to be exactly larger. I don't want to maybe make it equal. Exactly larger than epsilon. Okay. If F is 1 over R coverable, then it contains R disjoint set. Okay. So the very simple lemma is that if F is 1 over R coverable, then it contains R disjoint set. Why? Because we can just randomly partition x to R set. Okay, now we can randomly partition it. Now then, with high probability, W1, WR, with high probability, sorry, not high, meaning positive probability. Positive probability, we have good partition, such that for each I, it contains Si. For each Wi, it contains Si, just by union bound. Then, with positive probability, we can find the W1 equal to WR.
S1. Oh.
Yeah. Sorry, yeah. Yeah, for every I, yeah. Thank you for correcting it. For every I with positive probability, there exists a Si that is a subset of Wi. Once we have this good partition, okay, because this partition is disjoint set, then we get disjoint set S1 up to XR disjoint set. So basically, this we want to show. We want to show the set system. We want to show a pseudo-random set system is coverable. So basically, this is our idea. Okay, now we have the following lemma. F B.
So right now you're just trying to show it's one third coverable?
Yes, yeah, that's very simple. But sometimes in WSL system, kappa bounded. Actually, there's no bigger difference about R is equal to 3 or 4.
Sure,
Yeah, yeah. Bounded. Then probability. It's larger than 0.99. Where the size of W is equal to log W times X squared kappa. So I'm going to show this thing is that say F is a kappa bounded. Then with high probability, if we draw a subset W of size log W times X over square root kappa, then it covers the set with high probability means very close to 1. Okay.
So in this, you said this will be the source, this 1 over R will be the reason you get log W and
Yes.
constant. Which of the two R's is worse for you?
So,
Which of the two parameters, P or epsilon,
okay.
is the worst one?
I think P. P is the worst one.
You
Yeah.
would like it to be a constant, ideally.
Yeah. Yes.
Even
Yeah.
if it were a constant and the other one was 1 over R, it would,
Yes.
okay.
Yeah. This is the major part. And epsilon we can get improve it exponentially. I think epsilon is not the main problem, but kappa. Yeah. So yeah, I just pointed out this log W is the reason we cannot improve the log W barrier. So we have log W here. So as long as kappa is much larger than log W, say kappa is larger than log W squared. Okay, I'm going to improve a simple lemma. Say actually we can improve this square root to something very close to 1. Yeah, just by calculation log W squared times say 100. Then if kappa is much larger than log W squared, then we can get a non-trivial bound here. That's the reason we cannot improve. Yeah, that's the reason we get log W. Okay, so that is the main lemma. Okay, this one is stronger than sunflower. This one is stronger because this is a high coverable probability. Okay. Okay, so all of the things so far was known about 2 years ago. I mean, all of this is before this result. The main new idea in this paper, I mean, with Ryan and Kovan and Shah, is that we proved this lemma. Assuming this lemma, all of the other things are known before. Okay, so how do you prove this lemma is just by an very nice technique from Rasboroff's encoding. Raspberry used his encoding technique to reprove the switching lemma, hostile switching lemma, and that is really nice. And we use similar idea to prove this lemma. Okay, so basically we have a new random restriction lemma, but slightly different from Raspberry.
Change the definition of bounded a little bit to get rid of the square root on the k, right?
Yes. Yeah, just,
Log squared is fine for us.
yeah, or even 6 or 3, 4, just a constant. Yeah, log W to the O1. Yeah. Yeah. Okay, now we're going to show the thing is that, so, okay, so then our main technique.
Quick. So you're saying that for any W that's large enough, you get such a bound for a kappa bounded.
That's enough as large as this number.
Right.
Yeah.
Okay.
Yeah. So yeah, but I mean, if kappa is much larger than log W, then this is a non-trivial bound. If kappa say is smaller than W, then this is a trivial bound.
No, but when you say any W, it's a random W.
Yeah, random W. Yeah.
W of this size. That's what the probability is over.
Yeah, this is a uniform. Yeah, this is random seated over W. Sorry.
Right. Okay.
Yeah.
It's not from it. Oh, I see. Okay.
Yeah.
From the
Yeah, yeah.
Yeah. So yeah.
Right.
Now our main technique, just want to use one sentence to capture the high-level idea of our lemma. Main lemma is random restriction. So I call it random restriction. Simplifies random restriction. Simplify pseudo-random set system. Set system. Okay, so I just want to use one sentence to describe the idea of our proof is that random restriction simplifies the pseudo-random set system. I will formally define what it means is that, say, let F be a kappa set system, kappa bounded set system. Now we draw a random subset, W1, subset of W, X of size W1 is X over square root kappa. Okay, so there is no log W now. So draw a random subset of W1 of size X over square root kappa. Okay, so this is a random restriction. We call this a random restriction. Then with high probability. Okay. Now the following set system is equal to S minus W1. Okay, so basically this formalizes a random restriction because we want to restrict W1 is a subset of W. Okay, random restriction with high probability. This set system we're going to remove W1 from each set is simplifies to say this is simplifies to a W over 2 set system. And almost, I'm going to define what is almost means soon. Almost kappa bounded. Okay, now we want to say this set system simplifies to another set system. Say this is simplifies to a W over 2 set system, and also almost kappa bounded. Now once this is true, let's assume this is for a second. If this is true now, then we can draw W1, W2 up to log W. We can draw log W set system, and we can show with high probability the union of these sets covers the sets as. So basically this is okay. I mean, if this is true, then we can run, we can apply induction in this set system.
And you want to say that you think about it as a multi-set?
Yeah, multi-set. Yeah. Think about multi-set.
F is multi-set and
Yes.
so is that.
Yeah. We allow duplicate about the set, but we just care about the boundedness. As long as it's kappa bounded, we allow. Yeah, actually, all of this thing, I mean, all of this lemma applies to the multiple set system. Yeah, all of the lemma, yeah, we can allow. Yeah, that's a good point. Yeah.
Multi-set, and you have sets, but the same set can appear twice.
Yes, duplicate. Yeah, we have different. Yeah.
The sets are sets and not multi-sets.
Yeah. Yeah, we can allow everything actually. We just want to cover bounded. Yeah, whatever duplicating.
So three sets which are identical is a sunflower.
Yes,
Yeah.
yes, yes, yeah, yeah, yeah.
So, question. So I guess some people even know and some don't know the Haskell switching lemma and the proof. I don't want to go to too much detail. I just wonder. First of all, this is just for monotone.
Yes.
DNF.
Yes.
But you want a different property. You just want to shrink the size of the sets. You don't want to switch CNF to DNF.
Yes, yeah, we don't care
You
about.
just want to make them smaller.
Yes, yes, this is
When
a
it's, when
yeah.
it's bounded, it just allows it to
Yes,
shrink the size of the set.
yes, yes.
And it gives anything, well, I'll ask you at the end. Yeah.
Okay, yeah, so basically, I mean, so this is the idea comes from us that, but we don't really need to use the result of the switching lemma. Yeah, we just need the Raspberry encoding, yeah.
Just a small comment. I don't think you consider three identical sets as a three-sum flower. Because otherwise it wouldn't make any sense.
You do actually.
You do, why not?
You do. So the three identical sets would
Yeah.
be.
Yeah, just follow the definition.
No, I mean, it would be a three-sum flower, but lemma. Okay, but
Yeah,
okay, it doesn't
it's
really matter for the
good.
lemma.
Yeah, okay.
It's supposed to be clear how this is used inductively?
Okay, now, okay, let's simplify it. Okay, let's say if this is an exactly, okay, if this is exactly W over 2 set system and almost cover bounded, then we can run, we can apply it again because again, this is very, very close to the cover bounded. We can draw another W2, right? We can draw W2,
And these are the WO as a random. Right?
random, uniformly random, yeah, with high probability. Say we can draw W1, W2, W log W. Okay, so it simplifies again and again and again until log W, then it becomes, say, I mean, this becomes, yeah, sorry, this is small w. Okay, this is a capital W. This is a set and this is a size, yeah, the number, okay, I want to say. Okay, simplify it again and again. If we simplify it for log W rounds, then finally it simplifies to, it will contain an empty set.
What's bothering me is that these sets, each one had some W1 removed from them.
Yes,
But so so suppose you end up getting disjoint sets in the.
yeah, yeah. So
how do you
basically,
lift it back to the sunflower?
we're just going to prove this lemma.
Covered one set.
Yeah, cover one.
It has nothing to do with the disjoint
Oh,
sets
now we're
before.
just
It's not
covering.
really-
Yeah, we're just going to prove this lemma. Yeah. Yeah. So forget about the sunflower. We're just going to prove this lemma.
This lemma can actually not be better than log W to W.
Yes.
Problem, but
Oh, this lemma is incorrect for.
like we actually proved this lemma is actually tight.
Yeah.
Like,
Yeah. I
log
mean,
W to
this
W.
log W is necessary. This log W is not necessary in this study.
Okay.
Yeah. Yeah.
Wait, okay, sorry, just to say, after you sample these log sets,
Yes.
you say that
I say the union of them covers a set.
why?
Okay. So because, I mean, the claim is that W is the union of this set. Because, say, in the first round, we're going to remove W1, right? We're going to remove W1, and then, okay. Now, say, now for the second round, we're going to remove all of W2. And then for the W, we'll remove all of this side. Okay, after this log W rounds, if there exists an empty set in there, if, I mean, we get F capital log W. After the log W rounds, if there is an empty set inside, then we say it means there exists a set covered by the union of this set. Right?
So sorry, one second. Do you want to look at the link of W?
No. You can look at the
I mean,
link.
like if
If
No, we
just
are not looking at the
removing
link.
WI,
Yeah.
then you will still.
Wouldn't it contain all the sets? I mean, if you get a zero set system.
Yeah. There's a problem. Say there's a thing here. We simplify it here. Okay, actually, I forget. I didn't define what is simplify means. Simplify. It's not exactly a W over 2 set system and almost a cover. It is simplified. Yeah, sorry. Yeah, I should mention. Yeah, I first introduce what is the simplified mean. Yeah.
So maybe I should wait to ask this, but there's a
So over here you say you want S to be actually contained in W, right?
Yes, there exists as.
Oh, yeah, okay, never mind. I'm happy.
Yeah. Okay, cool. Okay, what simplifies means. Okay, simplifies means. So let me first first introduce a simple observation. Is that let's say S1 prime. Let's say we have two sets S1 prime. Sorry, S1, S2 from F. So this is a very simple observation. Is that
Just a question.
okay?
Before you get into this explanation, I mean, suppose we have this lemma.
Yes.
Do we see why everything is now done?
So what?
This will be done for each one of the sets, right? Each one of the sets in the covering.
Yes. So we can find the set that is covered by the W.
Yeah, so I'm just wondering, given this lemma,
Yeah.
how the rest of the proof will go before you define. I mean,
Okay. So basically, so once this lemma is true, then after log W rounds, we can find an empty set, right? Empty set
yeah.
in here. Now we just want to check how which set will simplify the two empty sets. So which means there exists a S in original F such that S set by removing the union of this set log W. Say this is the definition of right. By removing this thing, then we get empty set. So basically, it means S is a subset of W1 union W log W. And say for each of set has size x over log W over square root kappa, and we have log W set. Then by multiplication.
This will be just one of the
Yeah.
sets of the three, or
Yeah.
the other sets that will be covered by the other lemma.
Yeah.
Okay.
Yeah. Okay, now we're going to introduce what is the simplified means. Okay, so let me first introduce a simple observation is that okay, so let's say we have this system, and the given W1, given W1. Now in the WF prime is S1, we have two sets. S1 prime is defined. S2 is defined as S2. So this is by definition, in the new set system prime, S1, S2 will become S1 prime and S2 prime. So this is a very simple observation is that if F1 is a subset of S2 prime, then we can replace S2 prime by S1 prime. It does not change the satisfying probability. Covering probability, I should say. So if S1 and S2, we get S1 prime and S2 prime. And if this is F1 prime is a subset of S2 prime, then we can replace S2 by S1 prime. It does not change the covering probability. So this is very simple. So this we call it simplification, simplify. So because there are a lot of sets in this set system F prime, now we're trying to simplify that just by this rule as much as possible. Simplify this by this rule. Okay.
And replace, you just erase S2 prime, because S1 prime is already there.
Yeah, we can get another copy of S prime, S2 prime.
It's important to remember that you have two copies. You have
Yeah.
two.
Oh.
Yeah. So we want
We
to.
only need to find the set, so why don't
Yeah. Okay.
We don't need to remember how many.
Okay. So the reason we want to make different copies is that we want to show this kappa boundedness.
Kappa bounded
Yeah.
will keep track of how many you have.
Yes. So if you just going to replace, because we want to keep the kappa boundedness, so we have multiple sets. So actually, it's not really that matter. Okay. This is the definition of kappa bounded. Okay. Now, okay, so this is the simplification. Now we can define, say, given W1, we call S is good, say, if the following is true, if there exists S prime, has the following probability, S prime of W1 is a subset of S1. Second, okay, so we say given W1, we call S from F is good if there is another S prime such that this is true. And also the difference of S prime and W1 is bounded by W2, W over 2. Okay, so this is the definition. So so the intuition is that I say for all of the good S now, right? And by this rule, we can simplify S. We can simplify this set to S prime over S prime minus W1 because it does not change the covering property. And on the other hand, there is a good property is that the size of this set is upper bounded by W over 2. Okay. Okay, so basically our idea is that we use the encoding things to show for a random W1, almost all of the S are good.
What's
Yeah.
the encoding?
Oh,
When you say encoding, what do you mean?
This is our proof technique to prove this thing. I will show you.
This is the encoding where you encode S
We-
prime by.
Yeah. We encode all of the bad. So we encode all of the bad pairs to a small space. We encode all of the bad pairs. I will show it in a second. So this is our encoding technique. So we want to show. So what we want to show is that for a random W1, with high probability, all of the S are good. Yeah, this is our idea. So then how could we show that we're going to encode the bad pairs? So this is the idea. Yeah. Okay, now we want to show the thing. Okay, now it is clear how could we simplify this set system. We're just going to say for all of the good S's. So for the good S, we just replace the difference S and W1 replaced by S prime over W2. Yeah. Now, if for the bad things, we just throw it out.
So it's opposite.
Yes,
You
yeah.
replace S prime minus W by S minus W.
Yeah, we replace by S prime W. Say,
Replace the small ones by the big ones, or the big ones by the.
oh, we replace bigger ones by small ones. Yeah, we replace. Yeah. Yeah, we want to make it small. Okay. Now the definition is saying. So now what is the simplification now? So for good pairs, for good S's, we replace it by S prime minus W1. For the bad things, we just throw it out. Okay. Now say. Now it's clear the new set system is W over 2 set system because we threw out all of the bad things. Now, but what is the boundaries of the new set system?
The bad ones is just one way you just want to say you don't lose too much inside. Right?
Yes.
Yeah, so you don't care to throw half the settings and all something.
Yeah, we just want to, we want to throw out the things. Yeah, so the new set system is pretty simple. Lemma is that say the new set system is sorry. Okay, so the lemma is that say a very simple lemma is that say let's say F prime is the simplified set system. So this is the W over 2 set system. It's clear because we threw out all of the bad things. And what is the boundaries of this set system is the size of F prime over the size of F times kappa bounded. So this is just by simple calculation. We can show this thing is that the size of F prime over F bounded. So that's the reason I call it almost a kappa bounded. So but we can show this ratio is very close to 1. How close it to 1 is roughly like 1 minus kappa tuta omega w times kappa bounded. So actually our lemma is the following thing. Our lemma is that the set system f prime prime is, okay, one hand is W over 2 set system, and it's 1 minus kappa tilde minus omega W bounded. It's very, very close to 1, exponentially close to 1. Okay.
Sorry, question. When you say good, it's you want S prime in F, right?
Yeah, yes, good point. Yeah, sorry, I forget it. Yeah, S prime must be in F. Yeah. Okay, now this is our lemma. So basically, what is the idea is that encoding. We want to show for random W1 and random W prime, say, we want encode all of the bad pairs. Okay, we want to encode the bad pairs. So this is the idea. So what we'll claim is that random W1 S is good, is larger than 1 minus kappa minus omega W. Okay, so this is our claim. This is the lemma we want to show. And now, what is the idea to show this thing? We just want to encode the bad pairs. So otherwise,
Probabilities of a random W1.
and the random as uniformly
is
random.
in F,
Yeah, randomly choose a set from F.
random uniform chosen.
Yeah. So this can imply then by average argument, or we can show this thing. Okay, so that's the lemma we need to show. Okay. Okay, so this is the main technical part. Okay, so what is the sample space of this pair? Sample space is the size of the sample space is times. Okay, so this is the choice of W1 times F. I mean, this is the sample space of this distribution, and now we want to encode the bad pairs. How could we encode that? So let's say this is bad. Okay, let's say this guy is bad. Now, our idea is that we'll first encode W prime is the union of W1. Okay, the union of these two sets. Okay, we are going to output W prime. Okay, W prime is in our output of the encoding. Okay, the second thing, okay, we're going to order the set in arbitrary order, just in advance. Order the set, say order the set system F S1 up to Sm, so just order in advance. Find the smallest J, such that Sj is covered by W prime. Okay, given W prime, we'll always find the Sj. Sj is just the first set that covered by. Now we're going to encode what? Encode Sj union, intersect W1, the complement of W1. So we just encode Sj, the intersection of Sj and the complement of W1. So I'm going to draw a picture. Say if we have S1 and Sj and S. Now we'll first encode W prime the union. Okay, Sj union W1. Now, so for the Sj, we can.
Yeah, I mean, I don't know if the word encode is clear to everybody, but what you want to do, you have all the possibilities of W and W1 and S.
Yes.
And you want to say that the bad ones are just a few of them.
Yes.
So you just, you give them names so it will be obvious that this set is small.
Yes.
Relative to the original set. This encoding is just naming so that.
Yeah. Just to make an injection.
Obviously containing a much smaller set.
Yes. Yeah.
And the word encoding is not obvious unless people do.
Okay. Sure. Thank you. Yeah. Just to make an injection to the beta event to a small space, and we can bound the probability. Okay. Now, so there are two parts. Sj intersect W1 and Sj intersect the complement of W1. Okay, so Sj have two parts. The intersection of Sj and W1 and the intersection between Sj. Now we're going to encode this part. Encode this part. Okay, Sj intersection of the. Okay, the price for encoding this thing is about just the 2 to the W. So the choice is 2 to the W choice. This part. Now we have some property is that first because this is a bad pair, it means the size of Fj intersect W1 is larger than W over 2. So this is small w. This definition of bad. Okay. Now it means again because it's kappa bounded. Now we check this link. Sj intersect W1, right? Is much smaller than F. Oh yeah.
Sj minus W1.
No, intersect the W1.
The big part is.
Yeah, this is a big part. So we take this big part as a link, right?
Okay.
And say this is kappa W over 2 minus. So this link is small. Okay, sorry. Yes.
Sj minus W1 is a big thing, right?
Yeah, sorry. I should say. Sorry. Yeah. Thank you very much. Yeah. This is.
Could you go one step back? What is this 2 to the W that you said?
This what is the price to encode this pi?
Can you explain this?
Okay. Given W prime, we can recover Sj, because Sj is the first set to cover the set. J is always find the smallest J. Given W prime, we can recover J, Sj.
Okay.
Now we have Sj now. Now this is a subset. This is a subset of Sj.
Oh,
What is the price to encode a subset is just 2 to the W. Yeah, because this is a W set system.
given that we know Sj.
Yeah. Now, Sj is covered from W pi. Okay. Now, yes, exactly.
So actually, sorry, so can you say it even more slowly than me?
Okay.
So we start with W1 and S.
Yes.
We define W prime, it's the union of W and S.
Yes.
Then, okay, now
Um,
you define Sj to be the smallest S
yes.
that's contained in W prime.
Yes.
Smallest J in
The smallest.
this union.
In W prime, the union.
Yeah, in the
of W
union.
prime.
Yeah, in the union. Yeah. Yeah.
There is always one because that's it.
Yeah.
Ah, okay.
Yeah. Yeah.
Right.
Yeah. And also this set is large because this is the bad pair. Now we can, and also S is in this link. Sorry. Actually, S contains this here, right? Sorry. Right. So, sorry, a little bit different. Say, okay, what did I say? S is in this set, right? S because we have this property is that because Sj is the first thing. So I mean we have another property is S is a subset. Sorry. Sorry. Sj intersect W1 is a subset of S. So we have this property. Why is that? Because Sj is the first covered set. Just rewrite this definition. Just rewrite it. Yeah, just rewrite it in the different way. Intersect W1. Yeah, just rewrite it. You get this property. Now, yeah. Now the third thing is that I say now we can identify. So now we can recover this link. Given W prime and this set, we can recover this link. This link is small. Right? Is that clear now? Yeah.
Actually, I couldn't follow. Could you say it one more time? Like,
Okay.
what are you?
Okay, so I want to make an injection. Yeah, think about say we're going to make an injection from the bad pairs to something here, to the transcript here. So at the first we're going to output the W prime, right? So this is the in our output.
Maybe this encoding or injection, you want to make it to a product set where you can evaluate the sizes.
Yeah.
So the initial distribution is just a product set of two things, the W's and the S's. The bad pairs are an arbitrary set of pairs.
Yes.
And the encoding will be such, you'll get an upper bound on its size and it will be small because you'll see that it fits in a product, in several product sets of small sizes. So the first thing is this W1 union S, it's something
Yeah.
small, but anyway, that's the first part of the encoding of this term. The second thing is the intersection of Sj and W1 complement. This is a set of size W, so all possible subsets are just 2 to the W. That's
Yeah.
another product. So you multiply that 2 to the W.
Yes.
And that's how you go. That's how these tricks go. You take an arbitrary set of pairs in this case, and you just upper bound their size by saying they are mostly product of sets that when you know them or when you code it, when you know them, they reveal to you the whole original pair.
Yeah. It's always tricky here. So encoding part is always a little bit technical and tricky. Now, say this is in this link and this link is small, then we can use this number of, So now we can recover. So we can output another L. Sorry. We can output an L. Say this is in this set, in this number, kappa W over 2. So we can output an integer in this set, right, to identify the positions of S in this link. Yeah, just output the L. And the last thing is just encode this part, S intersect. Now given L, we can identify S. Now the last thing we are going to output this intersection is the last thing, 1, 2, 3. The last thing is just S intersect W1 complement. Now given this 4 part, we can recover everything. We can recover all of the bad pairs. Yeah, okay, what is the main save here? The main save is this part. We saved a lot. Kappa, because this is kappa bounded, and say we paid a little bit of price. But what is the main price here? The main price here is that we covered this set. We paid more price here. So just the analog to Rasborov's encoding. Rasborov's encoding, so this is part of the main save part. But we paid some price here. Okay, so this is not that important. But I just mentioned a little bit. Okay, so yeah, so just by calculation, we can upper bound the bad probability is just like 1 kappa to the minus 1 W. So this is the calculation. Yeah.
So it would probably be okay for you even if you didn't get this exponential bound. I mean,
Yes.
But I mean, even something like 1
Yeah.
like 0.1.
Yeah, just like,
fine.
yeah,
Even
just like,
constant fraction of S, or I don't know, 1 over log
Yeah.
W of S.
yes, this is much stronger with what we want. Yeah. I think this is the main thing. Okay. Thank you.